1918 paper was invariant variational problems. That was the title of a paper. So, I mention it only to emphasize the following. We are assuming we have a system of dynamical equations, equations of motion coming from a variational principle, namely Hamilton's principle. And then we see, she showed that if the quantity, the object being varied, the action has a symmetry is unchanged by some transformation, the fact that you have a variational principle leads you to a corresponding conserved quantity, integral of motion. So, I think the conceptually, I do not know, maybe this idea had not been there at all in the minds of physicists and mathematical physicists until her work. This is an amazing connection between symmetry and something which is preserved in the course of time. Just as an idea, it's just incredibly deep. And what I want you to appreciate is, it's not you write down any dynamics, any dynamical system obeying first order equations of motion. If they do not come from a variational principle, I want to emphasize, if you have dynamics, the kind of thing which Shamik talked about in his first and second lecture, if a system of equations in time, differential equations in time is preserved under some transformation of variables, all that you can conclude is that if you start with one solution of those equations and you apply the symmetry transformation, you will get another solution. That is all you can conclude. That is what preservation of the equations of motion means. But if those equations came from a variational principle, then there is a connection to a conserved quantity, and that was the greatness of Noethers' treatment. So, I want this to be very clearly understood. It is not the symmetries of any system of differential equations, it is the symmetries of differential equations coming from a variational principle. So, what we did yesterday was to show that if you have a point transformation, of course, at all stages I consider only infinitesimal transformations. We know that if you have a point transformation on a configuration space, this I have mentioned 2 or 3 lectures ago, it can always without any trouble be extended to a corresponding canonical transformation on the phase space. This is a very simple step, the extension of any point transformation on configuration space to a corresponding canonical transformation on the phase space. And in that extension, you see that when the coordinates change in some given way, the momenta change always in a linear fashion. The canonical momenta change in a linear fashion. And what we saw yesterday, that if you had an infinitesimal point transformation which preserves the Lagrangian, so it preserves the action, then you get the consequences that when the equations of motion are obeyed, there is a constant of motion. I will keep writing symbols corresponding to an infinitesimal transformation. I may omit this little parameter epsilon, put it in when you need it and remove it when you do not want it. So, the first consequence is that there is a constant of motion linear in the canonical momentum, and we have already seen that a point transformation always extends to a canonical transformation. This constant of motion generates that. And in this statement, so the symmetry transformation is a canonical transformation, and in making this statement there is no need to use the equations of motion. This is because the situation is really quite simple. So, the lesson here is that symmetry acts as a canonical transformation. It will map solutions of the equations of motion generally into new solutions, and the generator of that canonical transformation is the constant of motion. Usually, this kind of thing is called a kinematic symmetry. That is, when the constant of motion has such a simple dependence on momentum, linear in momentum, it comes from a point transformation, and the cases of translation invariance leading to momentum conservation, rotational invariance leading to angular momentum conservation are both examples of kinematic symmetries. All right. So, I would say that this is relatively simple stuff, and you please see whether this how this is handled in that article of 1951 by Hill from Reviews of Modern Physics, which two of the participants traced on the telephone on the mobile phone yesterday, not telephone. They gave you the reference to it also. Just knowing what I have said now, go back to that paper and see how it expresses this. Now, I come to the generalization. What I want to consider is a different kind, a more involved kind of transformation. In the case of point transformation, we imagined that the change we make in each generalized coordinate is a given function of the coordinates themselves. And we saw this is true for a rotation, it is true for a translation, let us say in Cartesian variables or any other variables. I want to discuss now the case where I imagine each generalized coordinate being shifted infinitesimally by some given function, not of coordinates alone, but q as well as q dot. These, and when we finish the story, we will give this the name dynamical symmetries, not like translations and rotations which lead to constants of motion like momentum and angular momentum, but more general. So, I have yet to come to the symmetry aspect. So, the first thing is, so let us imagine we vary every generalized coordinate by an infinitesimal amount, but by an amount with a specified dependence not only on the coordinates themselves, but let us allow some dependence on q dot also. Okay. Then it is the rule of Lagrangian mechanics that if the coordinates change in a given way, their velocity is changed by the time derivative of the change in the coordinates. So, what will this be? This will be expressions of this kind, and therefore, the result at the end can in principle depend on q, q dot and q double dot. We allow it. All right. So, this is the rule of Lagrangian mechanics. Now, we will say that this infinitesimal transformation is a symmetry of the physical system or of the Lagrangian if the change that it produces in the Lagrangian, and remember the Lagrangian is a function of q and q dot, if it turns out that when you change q in this given way and you change q dot in this given way, if the change in the Lagrangian has the form of the total time derivative of some object capital F, then we will say we are dealing with a symmetry. Okay. So, there are two generalizations I am making compared to the yesterday's discussion. We are allowing the infinitesimal changes in the coordinates to depend on the velocities, and then we are allowing the Lagrangian to change, but not in an arbitrary way. It has, there will be many contributions when you work out the left hand side using this expression for delta q and this for delta q dot, you will get some expression for the change in the Lagrangian. If all the terms put together conspire to take such a form as a total time derivative of some function capital F, then we will say we are dealing with a symmetry. Okay. So, this is a definition of a symmetry in a generalized way. Two steps of generalization. We have gone beyond point transformations and we are allowing the Lagrangian to change, but in a controlled way. All right. So, from this definition of symmetry, infinitesimal symmetry I should say, many consequences follow step by step. None of them is complicated, but what I will not derive them, I will describe them, and for those of you who are interested, please derive what I will say now yourself, or you can check the notes that I have given you. What are all the consequences that come from this definition of a symmetry? The first statement is that there is an associated constant of the motion. Oh, incidentally, I should emphasize, I am assuming it is obvious, when we make this statement, the Lagrangian behaves in this way. In this statement, no use is made of equations of motion. It is a statement about the functional form of the Lagrangian and the relation of that form to this given transformation. No use of equations of motion at this point. So, first statement that we find, the first result we find is that there is again a constant of motion. This combination P delta q minus the F which has appeared in the change in the Lagrangian is a constant of motion. So, this is a COM, and I will write it as some function g again of canonical variables. All q dot dependence I can replace by suitable p dependence. And of course, here when I say that this is a constant of motion, at that stage I must remind you, this is a constant of motion when the equations of motion are used. Of course, otherwise there is no meaning to constant of motion. So, I stress, in describing a symmetry in this way, no use is made of constants of motion. It is a statement of the form of the function, the Lagrangian. When we say that if we have a symmetry in that sense, there is then a constant of motion, this is Noethers theorem, at that stage we say we will find this is conserved in the course of time provided the equations of motion are obeyed. So, here it is a statement which is true when you assume the equations of motion. So, second statement, And well, addendum to this statement, for a general dynamical symmetry, a transformation in which the right hand side here does have a q dot dependence, this constant of motion will not be linear in momentum. It will be quite general, okay, non-linear. Okay, so that goes without saying. Now, what I can do is to take that transformation, knowing it is a symmetry, try to translate that transformation itself into phase space language. And here is the nice thing, you find a little bit of calculation is involved, more calculation than in the previous case, but it is not very complicated. You find these changes in the generalized coordinates turn out to have this form in the phase space language. And in verifying this or in proving this, I would just say there is no need to use equations of motion for showing this, and I would say it is slightly non-trivial, slightly compared to the previous case. So, this is roughly half of what you would call an infinitesimal canonical transformation, half only, because the rest is a rule for change in momentum. So, now I make the third statement. Third statement is, it is possible to define what we mean by the changes in the momentum variables under this kind of dynamical symmetry. It is a very straightforward definition. So, you can write down what you mean by delta p, and then you find, what do you think you find? The delta p also turn out to have the form of what you expect if you had an infinitesimal canonical transformation. But here, in establishing this, the equations of motion have to be used. Okay? So, the end result is that symmetries of this kind, dynamical symmetries, even such symmetries at the end of the story, when they are described in phase space, act as infinitesimal canonical transformations. The generator is the associated constant of motion. I hope you find these results interesting. As far as I know, these set of results, I do not know the attitude of most people when they experienced physicists, whether they think that these things should be so or that it is trivially so. I do not know what is the general feeling. I can ask Professor Burma, other senior people who may have taught the subject. It seems to me that most books in classical mechanics do not discuss these things, as far as I know. For myself, I learnt all of this in the course of some work I was doing. When was that? That was in 1975. I had just finished writing book with Sudarshan on classical dynamics. In that book, all of this is not there. Hints of it are there, but this was part of some other work I was doing. It appeared in Annals of Physics in 1976 or something like that. And I do not think there is any textbook, I mean I have not checked many of them, which show this beautiful triangular relationship. Here I want to say then, I draw that triangle again, the concept of symmetry can be extended to this kind of symmetry, which is not a geometrical operation on configuration space, but it is dynamical because it involves q dot. Every such symmetry leads to a constant of motion, and when it is rewritten in a natural way in the language of coordinate and momentum variables, it does have the structure of a canonical transformation, and once again it is the constant of motion which acts as a generator of that canonical transformation. So, this triangle of relationships, it is very simple in the case of point transformations. It involves a little bit of work, not a great deal, but some non-trivial work for a general symmetry of this dynamical kind. As I said, as far as I know, all this is not there in any of the books that I am familiar with. You can check, all of you have got the second edition of Goldstein. Actually, there is a later edition involving 2 more co-authors. So, I wish, actually one should have, Academies should have, not Academy, the course should have given the latest edition of Goldstein. I do not know why it did not.
Is Shamik here?
No.
So I'll speak on his.
Oh, sure, sure.
So he compared the two, and he found that the third edition is not simply added.
Oh,
things are not only added, but other things are subtracted.
Oh,
And
I see.
The subtractions were significant and
Okay.
not good.
I understand.
So he made
Very
a
good.
choice, an informed choice.
Very good. That is very good to hear that. So, then I just repeat, please, in the, I do not know whether this was there and it was subtracted. That I do not know, but please check it. Look at what you have now is before subtraction,
Yes.
what has been distributed. So, just you have the books in your hands, the registered participants. Please see whether there is a discussion of this part in the version which you have with you.
Yes, of course, the third edition has some subtraction and some addition also.
So you should check in the addition there.
The additions are probably of a different flavor.
Yeah, flavor, yeah.
Yeah, exactly.
Okay, okay, I see. So, certainly in sorry, in Sommerfeld's book such things are not discussed. I do not think so in Landau and Lifshitz either, and in the first edition of Goldstein, which is what I learnt in my infancy from 1960s, it is not there. Other more recent books, Saletan and Kromer, Theoretical Mechanics, a very nicely written book. Huh? Yeah. Yeah, but no, that is a later one. I am talking of a much 75 publication, Saletan and Kromer, Cromer, Theoretical Mechanics. Then there is a book by T.W.B. Kibble on mechanics, which is a very nice book by the way. It is quite compact. I give it as a small project. Just check all of these, whether this is given, treated in full detail in this way. My suspicion is no. Now, I used to think that Emmy Noether had also not considered such transformations. I used to think, I had this wrong impression, because it was not easy to access her paper. It was in translation, and as I said, only 2 years or so ago, Joseph Samuel gave me an English translation, good quality English translation of Noether's original paper, and going through it in careful detail, I find that she does have such symmetries also. Now, I used, oh my God, this is on YouTube, is it?
Yes.
Oh my.
That's true. Yes.
Is it on YouTube? Oh my. Okay. Anyway, all right. See, in my lecture notes, I have said, I used the phrase beyond Noethers theorem. I have used that phrase. I now can retain that phrase and say with some confidence, translating her results to the phase space language is not there in her treatment, as far as I know. So, please check that. But as I said, her paper is difficult to go through. It's very, there is a word called turgid. You know what that means? Something which is like a very thick liquid, but not quite liquid, and it's not solid, but it moves very sluggishly, like that kind of thing. Yeah, it's not transparent. And also the language of 100 years ago, this year is a centenary of her paper, it is very different. Even after translation, you find it is not easy to read, but it's a classic of mathematical physics literature. So, please do, those of you who are more adventurous, please have a look at it. So, I just want to make some concluding comments at this point, that so the most general infinitesimal symmetry of a Lagrangian system is the dynamical symmetry. It is described in the way I have written. It leads to a constant of motion. When it is recast in phase space form, it again appears as a canonical transformation, and the constant of motion serves as the generator of the transformation. So, this relationship among three different concepts I find extremely deep and very, very impressive in my mind. Okay. In quantum mechanics,
So how is this definition of dynamical symmetry related to our basic notion of symmetry?
What is the basic notion of symmetry? You tell me, please.
Say geometric symmetries.
So, geometric symmetries are the ones I described yesterday, point transformations. They are called kinematic symmetries. They are symmetries which are described as mappings of configuration space onto itself. All right. These I am allowing it to go beyond that. So, here symmetry in this sense, because it is dynamical, it cannot be visualized in geometric terms. So, a symmetry now means a well defined transformation, a rule for changing Q in a definite way, which has the property that it preserves the equations of motion. That is all that symmetry means here. If the equations of motion come from a variational principle, you have these consequences, that there is a constant of motion. This connection between a symmetry and constant of motion does not happen if you have an arbitrary system of differential equations. It has to come from a variational principle. That is why I started today with the title of Noethers' paper, Invariant Variational Problems, in German, of course. Okay. So, the key input is that your equations of motion are of a way, come from a Hamilton's principle basically. In that case, these two get connected. This part, I should patent it, I suppose. I don't know.
Write a paper on it. Maybe you have.
It is there in the lecture notes I have distributed to all of you. How do you find out these things? But what did you ask Google to do for you?
1976.
Ah. Oh, what did you put there? In
Search I put just Annals of Physics 1976.
How did you say Annals of Physics? I didn't say it.
You did.
I did. Okay, I forgot. Yeah. That's the one. That's the one.
I go to Saigon if I can't get it.
Okay, that's the one. That's the one. It was in print. In
Tell us all later how to do things.
yeah. So that was what I was referring to. Okay. Yeah. Huh? That is not of this kind.
That is not of the previous.
Yeah, yeah.
So in that case, spherical symmetry is there. So I will change delta Q such that it's compatible with the spherical symmetry.
It describes rotation.
Independent rotation.
Yes, yes.
So that's how it connects. In the previous one, it connects with the geometrical.
Yes, yes. Here it is not geometrical. That's why I give a different name. Yeah, yeah. Now I just want to give you a very trivial example, but you will learn something from it. We know that if the Lagrangian has no explicit time dependence, the Hamiltonian is a constant of motion. Prove it. It is a case of a dynamical symmetry. Okay, prove it using the idea. Find out what should delta Q be to lead to the constant of motion being the Hamiltonian. Anybody want to guess immediately? It's a translation in time. So imagine the delta Q is the change in Q in a time epsilon. Then what is the right phi? Huh? It's a very simple, nice example. Well, I will write it. This is the effect of an infinitesimal time translation. All right? So I am giving you the answer. According to the rules of Lagrangian mechanics, the changes in the Q dot are Q double dot. If the Lagrangian has no explicit time dependence, verify, simple exercise, that this is a dynamical symmetry. That the change in the Lagrangian under that change in Q and that change in Q dot is a total time derivative. Do you know what it is? In that case, finish. So it's a symmetry. If the Lagrangian has no explicit time dependence, translation in time is a symmetry. And what is the associated constant of motion? I have written it somewhere here. PQ dot minus Lagrangian. What is that? Hamilton. So relating energy conservation to time translation symmetry is an example of a dynamical symmetry in my language. It goes beyond kinematic symmetry. So, and the Hamiltonian for non-relativistic systems has a non-linear dependence on momentum. It is p squared by something for each particle and then a potential. So I think all these things are nicely illustrated. I am only saying that the symmetry is first defined in a certain language, in a certain way. For geometrical symmetries, it was a mapping of configuration space onto itself. You then extend its definition, make it act on other things. When you have done all that, you ask, can I express all that I have defined as the symmetry operation in the language of phase space? When that is done, it turns out to be a canonical transformation. That relationship persists in this case. All right? But I must stress, I will not go into details, this discussion of a dynamical symmetry remains at the infinitesimal level. Okay. You can't say what is the finite form of this symmetry transformation. For a rotation, a geometrical thing, you can make an infinitesimal rotation, then you can do it many times and you end up with a finite rotation, which is also a symmetry. Here it is much more complicated. If you want to go beyond first order, then obviously it will involve Q double dot, Q triple dot, it will Q, the new Q will involve the old Q at an earlier time and so on. I don't want to go into that. But at this stage, it is all very nice. So I gave a reference to an article in Resonance a few years ago, 2011. We have described many such symmetries for simple mechanical systems. For the harmonic oscillator in say isotropic oscillator in 2 or 3 dimensions, not only is there rotational symmetry which leads to angular momentum conservation, but there is greater, higher symmetry which is very specific to the harmonic oscillator. It leads to constants of motion quadratic in momentum. They are all of this kind, and all the details are given in that resonance article. For the case of the Coulomb or Kepler problem, there is a very special extra symmetry beyond rotational symmetry, and it is called I don't know the name. Huh? There is a constant of motion called the Runge lens vector. Huh? Not Kutta, that is a numerical approximation. Yeah, I know. So this is a vector, it's known from a long time. It played a very important role in Pauli's work soon after Heisenberg's work on matrix mechanics. In November, December of 1925, Pauli showed that Heisenberg's suggested new approach to quantum mechanics solves the hydrogen atom problem. He got the quantization rules before the Schrodinger wave equation was constructed, and in that work he used this classical known non-kinematical constant of motion special for the Coulomb problem. So this also is a result of a dynamical symmetry. There is a fairly complicated dependence on momentum. It is not linear. Anyway, it is all in that resonance article. Okay. So okay. So what I want to do now, just a few minutes, is to change track completely. See, it is also a psychological situation that because I have this feeling that this is not there in any textbook, I have a what is it called proprietary attitude. So I am reluctant to go and check in the library book after book. Is it there anywhere? I have just been mentally not willing to do it, but in all honesty, if some of you can do this for me and let me know the actual situation, my soul will rest in peace. You understand what I mean? There is a very beautiful talk by Dirac when he was given the Oppenheimer prize. Soon after Oppenheimer passed away, Dirac was given the first Oppenheimer memorial lecture, and there he talks about the hopes and fears in doing physics, and he says that when he had discovered the Dirac equation, he did first order perturbation theory with his new equation to check for the the energy values of the hydrogen atom, and he got this fine structure correct to lowest order. And then he says he did not try to go further because he was afraid he might not get the correct answer, and if that had happened, the whole thing would have to be abandoned. So he stopped at that stage. And who came and who is it that had no such fear, because it was not his equation? Darwin. Darwin was the one who solved the Dirac equation for the Coulomb problem exactly, and it turned out it works perfectly. And it's a pretty complicated piece of work. Relativistic quantum mechanics, it involves a lot of work. Okay, so I am following in that tradition, and all of us have this feeling. Huh? Yeah. Okay. Okay. So now I just want to say a little bit about this Dirac theory of constrained systems. Just to give an indication, in the lecture notes that I have given to you, distributed to all of you. I might even mention those lectures of 2011 or something. I gave at Hyderabad Central University, basically at the invitation or urging of my colleague Professor Chaturvedi. He is now at IISc Bhopal after retiring from Hyderabad, And he has used those lecture notes of mine to teach a course in that 5-year integrated special, I don't know, advanced classical mechanics or something. He has found it useful. And you know Sudhendu Rai Chowdhury, who used to be at Delhi University, you don't know him. He is retired, he is now in Bhopal, and yesterday Subhash Chaturvedi told me Rai Chowdhury said that he has been asked to teach this course on advanced classical mechanics, and he was wondering what to do. And so Chaturvedi said, why don't you try this? So he's going to give the course on that, based on that. So I am very happy that what I did and wrote up with a little bit of care, it is being found useful. Now, the last part of those lecture notes is devoted to a description of what is called the Dirac theory of constrained systems. So I just want to tell you a little bit about it, a kind of motivation, and then if you are interested, you can have a look. This subject has a very long history. Now, in all the discussion up to now, we have always assumed that the equations which we traditionally think of as the point where canonical momentum is defined, we have always assumed that the Lagrangian is such that these equations allow us to invert them, in the sense that we are able to write every q dot as a function of q's and p's. We have been assuming this in non-relativistic systems. This is always true. Now, from very early times, 1930s onwards, Dirac had been interested in systems, mechanical systems, Lagrangian systems, where these equations cannot be inverted in that way. Q dot, you are unable to turn these equations inside out, so to say, and write every q dot as some function of q and p. You never face this problem in non-relativistic mechanics situations, because the kinetic energy has a very simple role. So, from the historical point of view, in 1932 or so, he wrote a paper in a journal which is quite remarkable in some ways, Proceedings of the Cambridge Philosophical Society. It's a small scale journal. It was in those days not like the Proceedings of the Royal Society, for example, but now and then some gems would appear in that journal. I don't know if this journal still exists. It probably does. Proceedings of the Cambridge Philosophical Society, PCPS. So, sometime in 1932, he wrote a paper in this journal exploring some properties of systems, Lagrangians, for which this problem happens. When a Lagrangian is such that these equations cannot be inverted, he gave them a name, singular Lagrangians. So, I mention this only to say that it was in his mind to develop methods in a systematic way to deal with such Lagrangians. If you have this kind of problem, you are already stuck right at the beginning. What do we mean by phase space for such a system? Because if you can't invert, where do you go? What do you do? And so it was in his mind for many years. Then in 1949, there was a Canadian Mathematical Congress, the first Canadian Mathematical Congress held at the University of British Columbia in Vancouver. And in that Congress, he gave a series of lectures. And those lectures were published as a paper in a new journal set up around 1950 called the Canadian Journal of Mathematics. Canadian Journal of Mathematics. So, the first volume of this journal has a long article based on the lectures Dirac gave at that Canadian Mathematical Congress. The title is Generalized Hamiltonian Dynamics. That is the title, Generalized Hamiltonian Dynamics. References, well, it is easy to find. This paper of Dirac, the first one was in 1950, and then there was a follow-up paper the very next year, I think. In these two papers, first paper basically, he created a beautiful new theory within formalism of classical dynamics to deal with Lagrangians which are singular in this sense. So, a Lagrangian is singular if it does not allow you to solve for every q dot in terms of q and p. So, in this work of Dirac, he gave a beautiful an algorithmic approach, you would say today, how to define phase space, how to define Hamiltonian, what are the new features, what are the new concepts which you have to create to handle such systems. Now, this paper of Dirac, this generalized Hamiltonian dynamics, it is not easy. It is written, of course, in a very carefully constructed way, but if you do not have adequate background, it is not easy to understand why he is doing what he is doing. At least that was my experience. I have spent many years reading that, trying to understand that paper. And one physics motivation for this whole theory is the following. Suppose you have a symmetry of the type I have been describing up to now, whether it is a kinematic symmetry or a dynamical symmetry. Suppose in the symmetry transformation there appear arbitrary functions of time. This is a very important conceptual point. Supposing that the symmetry has this form, an infinitesimal parameter epsilon times a function of q and q dot, for example, but I tell you epsilon can be any arbitrary function of time. Suppose there was a symmetry for a Lagrangian of this nature, it follows that it has to be singular. Symmetries which involve arbitrary functions of time necessarily means that the Lagrangian is singular. This happens in electrodynamics. Why? Because you have the freedom to perform gauge transformations. Gauge transformations involve arbitrary functions actually of space and time, but the part is the time. General relativity, general changes in space-time coordinates involve arbitrary functions of time. So, Yang-Mills theory, those of you know, same story. So, it is not a rarity that a Lagrangian might be singular. Whenever you have symmetries involving arbitrary functions of time, it will automatically mean the Lagrangian is singular. And guess what? The second part of Noethers' paper is exactly this problem. What if the transformations preserving the variational principle involve arbitrary functions of space-time? She discusses all that in her own way, but never bringing in the phase space aspect, as far as I know. Okay. So, you see that the subject has a very rich history, and these papers of Dirac, as I said, they are demanding, better not to say difficult, but demanding. So, in 1964, he gave a set of lectures at a university in New York City which no longer exists, Yeshiva University. And it is a very famous set of lectures. Those lectures, the title is Lectures on Quantum Mechanics. It is appeared as a book, it is freely downloadable from the internet. Lectures on Quantum Mechanics, 1964 lectures given by Dirac at Yeshiva University, published by Yeshiva, but the university does not exist, the lecture notes exist. Right? So, you can download it, it is hardly 80-90 pages length, But in those lectures, he gave the contents of his 1950 paper, the Canadian Mathematical Congress, that paper, in a more easily understandable form. And then many others have followed up on that. There is a beautiful sort of review article by Reggie. How many of you have heard of Reggie? Tullio Reggie, huh? Yeah, same, yeah. Reggie, just for historical interest, he was a contemporary and classmate of Sudarshan. He was also a student of Marshak at Rochester. So, in 1974, the year that I wrote that paper, there is a beautiful review by Reggie, Hansen, Reggie and Teitelboim, Generalized Hamiltonian Dynamics. It gives all the examples of such singular systems. It gives electromagnetic theory, general relativity, Young-Mills theory, string theory. All of these are discussed one after the other. It's a very nice review article. My own work, which you traced so easily, was to see how far one could go with this kind of picture for singular systems. And it seemed, from my understanding of the subject, this part Dirac had omitted. He told us in his yeshiva lectures and in his original paper how to handle the equations of motion for singular systems, how to set up the phase space, what are all the new features which come. But there was no explicit discussion of what happens to symmetries of such a system. So, that is what I tried to work out in that 1975 paper of mine. So, this is a very rich subject, and I have given an account of it in the lecture notes which have been given to you. So, I will stop at this time. I have to go for security clearance very soon. So, let me conclude by saying that once again I would like to thank Professor Burma and Gupta for inviting me to lecture here. It has been a real pleasure, also because the Vice Chancellor Maharaj is the one I passed in his PhD exam. Right. So, though the subject itself is very old, classical mechanics, it's mainly formalism. I have tried to bring out features of the subject which, though you have studied classical mechanics any number of times, some aspects you may not have realized or noticed. So, that has been my aim. So, thanks, and let me go in peace. Yeah. That's enough.
So, on behalf of the organizers as well, we would like to thank Professor Mukunda for not only sparing the time, that is, but really giving an edifying set of lectures.
Thank you.
It's many things in context that were certainly new to me, and perhaps some of you as well.